Yeah. So the purpose for performing this closing operation before doing anything was to collect all the unit clauses before we start our algorithm. And why we are going to do that? So as we can collect these unit clauses, so that means we have a set I which contains all the unit clauses, right, that are either directly present in the knowledge base or were derived from the knowledge base using unit resolution, right? And if we do that, what we can do, we can set, we have to set, I should not say we can, we have to set all the unit clauses that are belonging to I to be true, right? So let's say our unit clause I set contains say A, negate B. So these are unit clauses, or say negate C, right? Now, as their unique clauses, you have to make them to be true. Otherwise, your knowledge base will not be will be having a contradiction. So in order to make this to be true, I have to set A to be true, B to be false, and C to be false. And I do not need to perform any decision operation. And what is the cost involved with any decision operation? The cost involved with any decision operation is that if your decision, a particular decision goes wrong, you have to backtrack. But here you are left with no option. You have to forcefully assign true to A to true, B to F, and C to F, right? So you do not have any option for decision. And as you do not have that, you do not need to have a backtracking. Either you fail or you succeed, right? So that's why we are collecting these unique clauses under this I set. And what is remaining? The remaining is the residual set of, so we are conditioning this knowledge base using this set of unique clauses, right? And what will this contain? This will contain the literals for which we have to take the decisions, and which is a smaller subset of all the particular variables or literals that are there in your knowledge base, right? And for this, you need to do backtracking. But for this I set, there is no need for backtracking. So that is the particular motivation for collecting these unique clauses before we start our algorithm, right? And in the last class, we have given an example how really we can compute this I from a given knowledge base. And if we can compute I, we can condition the knowledge base with I to get our set of gamma clauses, right? Which is a kind of residual clauses, right? Let us now go forward with the algorithm. So algorithm is will be a kind of very basic variation of the DPLL minus algorithm, and the input to this is a CNF delta, right? So the first thing we'll be doing, we'll be performing this unit resolution, unit propagation. So this we can get by performing unit propagation over delta, right? Now, if we see that your gamma is empty, right? So what does that mean? That means that I did not encounter any contradiction, right? So if that is so, what we will be doing? We have to return the assignments for which at least we do not have any contradiction. And what is the assignment we have? We have the assignment in the form of I. So what we'll be doing? We'll be returning I, right? Else, if your the residual knowledge base gamma, if it contains an empty clause. What does that mean? We know that, right? So this is a case of contradiction. So then we have to return unset, right? Now in this part, we have already collected I and forcefully assigned truth values. Now, if you have set up literals to be L, I should name it differently. Okay, now the L is fine. Or yeah, so let us name it to be Y. So if we have all the variables to be Y in our knowledge base, then what are the remaining variables? The remaining variables are Y minus L. And for this Y minus L, we have to make the decisions. And how do we make the decision? So you pick up one variable from this and set Y to be true in one branch, and in other branch, you will be setting Y to be false. So that's what we'll be doing. So what we'll be doing now, we choose a literal X in that appears in this gamma, right? Now, so we'll be performing the simple steps that we have done earlier, the similar thing. We'll condition this on X, positive literal, right? And if we see that this is not unset, and when we return unset to this, what we'll be returning? We'll be returning a set of assignments, right? And our final return would be the union of this. So this is a solution to the sub problem, which is this gamma conditioned over X. And we have to add I to it, because I is there for I we have done the truth assignment, and we have assigned positive value to X. So this is what we'll be returning, right? Else we check whether if we perform DPLL on negated X, if this becomes unset. So this is the second branch. So this branch we are taking, right? So then what we will return? We'll return L, I, and negated X, right? And this is the end of the algorithm. So this is similar to what we have done earlier in DPLL minus, but we are doing an extra step here by cluster or classify the literals into two sets. One is the I set and other is the Y minus I set. And for this, we are forcefully assigning the truth value. And for this, we are making the decisions. Right. And this decision part will be implemented using this recursive form. So I hope this part is clear. If there are any questions on this, I'd like to answer. Otherwise, I will move forward. Okay, great. There is a comment. Okay, Anupam, so I don't know. Shorashi, is my audio coming? Hello?
Yes, you are audible.
But some of them are telling that I'm not audible. Anupam and Varshishta. Okay, they flagged that I'm not audible. So are you okay, Anupam? Okay. So now what we have done, we have talked about SAT solvers using inference, which was kind of DP. And you have talked about SAT solver using search, which is in the form of DPLL. Now you want to use the best of both the worlds. We'll be combining inference and search and come up with a different class of algorithms, right? So now we are going to talk about SAT by search and inference. And basically, this is the kind of technique that is the basis of most of the modern SAT solvers, right? So we'll be, I think, having a demo session in the second half today. There we'll be talking about GSAF, which is a kind of tool which is based on the algorithm that combines the search and inference together, right? Now, before going to this search and inference combination, so let us try to see a limitation of DPLL, right? So let us try to talk about limitation of DPLL, and actually that will give us the basis of designing these kind of algorithms, right? So the basic limitation of DPLL is that it is based on something what we call as chronological backtracking. So by that name, you can guess what we mean by chronological backtracking. So we are performing assignment in a specified chronology, right? So true. We are following left branch, left branch, left branch, and then when we get a contradiction, we backtrack in a reverse chronological order all the way to the root, right? So this is what we call as chronological backtracking. So what do we do there? We try in a given level for a given variable. We try both the values. Try both the values of variable x, right, at level L, right? And this is a kind of step where we use the recursion. Recursion using not of x, and so we condition this and delta not of x as we did earlier, right? Now, if we hit a contradiction, what do? We backtrack to level L-1, right? And in this process, what else we do? We undo all the intermediate assignments. Intermediate assignments, right? Now, again, it might so happen that you choose a different path in L-1 that gives another contradiction. So we try out. So let me put it in different intention. So try out different value for the variable L-1, right? And again, if we get a contradiction, we backtrack to level N-2 and we keep on doing this, right? And finally, what do? We move all the way to the level 0 right? And if we see that the other decision in level 0 that gives you a contradiction, then you say your knowledge base is unsatisfied or your knowledge base is inconsistent, right? So the point that we are trying to make here, that backtracking at level L is performed only after we have tried both the values at L plus 1. And that is really what we call as chronological backtracking. And in this process, we do not really keep track of the information about the particular contradiction that triggered the backtracking. So there might be different scenarios in which the contradiction is made and that triggers the backtracking, but we do not really keep track of that in DPLL, the traditional DPLL. So let me try to illustrate the idea and try to make it more concrete using an example. Great. So let us take our knowledge base delta to be, so we have something like this, A, B, then we have BC, then say not of A, not of X, Y, then we have not of A, X, then Z, not of A, not of Y, Z, not of A, X, not of Z, then we have not of A, not of Y, not of Z. So this is our knowledge base, right? And given this, we can draw the termination tree for the DPLL as we have done earlier. So I'm not explaining this. I hope you can do this. So we take true branch, then being in B, I can take true, C, true, then let's say assign X. As we assign X, we get, and we assign true to X, we get a contradiction. So we have a contradiction here, right? Now we can follow now you'll be following the other branch, and here also you'll be getting a contradiction. So I'm not doing this, you can check it out, right? As we get contradiction in both the edges, we'll be backtracking to C and assign, say, F to C, right? Now, as we assign F to C, we have a choice for X, and let us assign T to X, and if we do that, we'll be getting again another contradiction, and we are left with the option T X equal to false, and if we do that, we get again a contradiction. And as we said, now what we'll be doing, we'll be backtracking to B. And what is the option left within B? We have to assign B to F. Now, if we assign F to B, we have to forcefully assign C true to C in order to make this to be true, right? So you can check it out. Now we do not have a choice decision to make for C. As we do not have a decision to make at C, we'll be making a decision for the next variable X, right? Now, if we set X to be true, then again we get a contradiction. So we get a contradiction here, and if we say F, we get another contradiction here. And then we do not have any choice left in B. We'll be backtracking to A, right? And assigning false here. So as soon as we assign false here, we force B to become true and our knowledge base becomes satisfiable at this point. Right? Now let us try to observe something. So whenever we are taking this branch, so we are setting A equal to true. So while we are setting A equal to true, we revise this, the third clause. How will it be revised? So what will be kind of this third clause conditioned over A equal to true? Can anybody tell me? So I'm conditioning this knowledge base over A. That means A equal to true. So what will happen to the third clause? So will anybody respond to this? Very simple to follow. I don't know why you are not responding. Harshdeep?
Yes, sir.
So if I set A equal to true, what would be the revised state of our third clause?
So not XY.
Not XY, exactly. Thank you. So let us name this to be 3 prime. Right? And similarly, you can check it out. If we see that a fourth clause will be translated to this. This fifth clause will be translated to not of Y, Z, and sixth clause will be translated to X, not of Z, and seventh clause will be translated to not of Y, not of Z. Right? Now after that, this B and C, they do not have that much of effect. So I'm just skipping them. So we set A equal to true, C equal to true, right? Now, as we set X equal to T, again, we can see that this 3 prime will be converted to Y. So let me save some space. So we are setting X equal to true, or 3 prime will become Y. And let us name this to be 3 double prime. And say if we combine, say 5 prime and 3 double prime. So what we will get, we will be getting Z, right? Basically, we are trying to combine these two, right? So let us name this to be say 5 3 double prime, right? And then we are combining say 7 prime with 3 double prime. And what we'll be getting, we'll be getting negation of Z. Let us name this to be 7 3 double prime. And if we combine this 5 3 double prime and 7 3 double prime, we get a contradiction. Right? Now, as we get a contradiction, we'll be setting X equal to false. Right? As we set X equal to false, so the fourth clause will be converted to uh, Z, because we have set A equals to true and X equal to false. So Z should be true. And let us name this to be 4 prime. So we have 6 prime and 4 prime. If we combine them, we'll be getting X. And let us name this to be 6 4 prime. And we know that we have already not of X here. So not of X, and if we combine that with X, then we'll get a contradiction. So what we are doing in this path, we are doing delta over A, B, C, and X in this path. And in this path, what we are doing delta A, B, C, and negative X. So that means, what does that mean? That means that we have a contradiction at the level of C itself. So as soon as we condition this knowledge base on ABC, we should have identified the contradiction, but DPL does not see that. DPL does not see the contradiction at this level. Also, if you can perform similar kind of exercise, we'll see that delta AB negative C X and say delta A, B, C negative X will also, both of them will also lead to contradiction. So what does that mean? That means we have a contradiction for delta A, B negative C. Now we have a contradiction in delta A, B negative C, and we have a contradiction in delta ABC. What does that mean? That means we have a contradiction in AB itself, but again, DPLL does not see it. And finally, we can see that the real culprit for this contradiction is while we set A to be true. So this is the real culprit. This is the real cause of contradiction. So this is the real cause of contradiction, but DPLL does not see it. As it does not see it, it blindly perform this backtracking at all the levels, right? So in summary, DPLL does not see or keep track for which particular assignment or decision we are having the contradiction. Who is the real culprit? That does not observed by DPLL, right? And that's why you see that we have 1, 2, 3, 4, 5, 6 contradictions. We have 6 contradictions before DPLL realize that A equal to true is not our right option, right? So let us see what we can do to improve this situation. So the first concept that we like to bring in is what we call as non-chronological backtracking. Of course, chronological backtracking is the kind of limitation, and to counter that, we'll be having this non-chronological backtracking. So what we'll be doing here, so let me try to first put forward the intuition and the philosophy behind this, and then we'll be going to implement the idea. So we'll try to find out the set of variables that are actually involved in contradiction. So find the set of variables that are actually involved in contradiction, right? And actually this idea was initially proposed as a technique for CSP. And that particular technique, what we call as back jumping. So we jump back to a particular assignment, which may lead to contradiction. So we will be skipping all the kind of assignments in between, right? And what was the kind of motivation behind doing this? The motivation was that, well, while you are solving the CSP, so you are basically moving into inside a search space, right? And it might be a case that you get into a portion in the search space that does not contain a solution. So this is the kind of region of the search space that does not contain a solution. And through some assignments, you are ending up into this region. So what do you want? So one way would be, okay, you forage through this sub-region, and finally, after you have exhaustively searched all the points here, then you realize that we do not have our solution here. Then we uh, go out of this. But it would be great if you can quickly come out from this region that does not contain the solution. And that is implemented using this idea of backjumping. And this idea has been borrowed to SAT solver from the CSP domain, right? So what is the philosophy? The philosophy is that you backtrack to a lower level L without trying every possibility between the current level and the level L. So what we have done, we have performed this assignment, and assignment. Now this is your current level C, right? Now you know that you have to do backtracking because here you have exhausted all the possibilities, right? So you don't want to backtrack chronologically like this. So if you understand the real culprit is this, I will like to back jump directly to this without considering these revisions, right? So this is the philosophy, right? Now with this philosophy, let us talk about the intuition. And the intuition will lead to our solution, right? So what is the intuition? The intuition is that first identify every assignment that contributes to the derivation of empty clause, right? And whenever we have got an empty clause, we have a inconsistency, right? So identify every assignment that leads to derivation of empty clause. And empty clause means contradiction, right? And these set of assignments, we name this to be a conflict set. The set for which we get a conflict. So that's why this is named as a conflict set, right? And then what will be doing? We will backtrack. As we have a contradiction, we need to backtrack, but we'll not be backtracking to the immediate previous level. We'll be backtracking to the most recent decision variable that appears in the conflict set. So this conflict set, one thing that you need to maybe at this point you can hypothesize, but going forward we will see that this is really true. That it will, so let's say you have made an assignment from A to B to C to X as we did earlier, right? Now, in the conflict set, we will not be having this B and C because they are not participating in this contradiction. So only variables that are participating in this contradiction is A and X, right? Now, as we are exhausted with all the options in X, we'll be directly backtracking to A, which is the most recent decision variable in the conflict set, right? And then we will try out its different value. Right. So let us take the same example and try to illustrate the idea, what we are trying to see. Okay. So we have A, we have started with A, we have assigned to value T, we have B, C, then X, And in the process, we are making the assignment to be A equal to true, B equal to true, C equal to true. And if we assign X to true, so what will happen? From this assignment, we can infer that Y is equal to true and Z is equal to true. So this is what we are inferring. So these two we are inferring, not deciding, right? And at this point, if we set X equal to true, we will get a contradiction, right? That you can check, right? Now, what is the conflict set we'll be getting here? The conflict set will contain A equal to true, X equal to true, and Y equal to true, Z equal to true. So this is the kind of assignment for which we are getting our conflict, right? Now what we'll be doing, we'll be trying out the different value. Now if we set Y X equal to false, so we have A equal to true, B equal to true, C equal to true, and X equal to false. What we can infer? We can infer that Z equal to true. And of course, our contradiction. So you get a contradiction here also. So you get CS2, which is our conflict set 2, to be A equal to T, X equal to false, and Z equal to T. Right? Now in both of these, what we have done, we have exhausted with all the options at X equal to true and false. So that means what is the most recent decision variable for which we have not explored the other option? That is basically A equal A variable. And from this point, we'll be directly backtracking to A and try out the value F for it. And what we are gaining here, we see that we are encountering only two contradictions before we do this backtracking. And we know that A is the real culprit, right? And this is in contrast with the DPLL algorithm where we have got 6 contradictions before we realize that A is the culprit. So basically the idea is to find the culprit, the real culprit, right? Now with DPLL we found this culprit after doing 6 contradictions. And in this particular non-chronological backtracking, we are able to find out the fact that A is the culprit by just doing only encountering only 2 contradictions, right? Again, I have left some of the things unaddressed, like say, how do we rule out this B and C? We'll do that later. Just now developing the background, right? So the next idea that is very empowering is what we call as empowering clause. And this is for unit resolution. Again, let us talk about the intuition first. So the first intuition is, so these empowering clauses are the clauses that are implied by delta. But they are not explicitly there in delta. So these empowering clauses are present implicitly. Right? As they are present implicitly, they do not participate in the inference procedure. Right? Now, what will happen if we add them into our knowledge base explicitly. So if added, of course, explicitly, the unit resolution might have or may have additional information. And this additional information can be leveraged to find out these conflicting clauses and other things very efficiently. So our ultimate goal is to perform this non-chronological backtracking, but we need to devise certain techniques that will help us to perform this non-chronological backtracking, right? So one particular idea is that if we can find out the contradiction pretty early, then we can perform the backtracking, non-chronological backtracking from there itself. Don't wait for later. Right? So one such example from the given knowledge base that we had is that this delta implies these particular clause. Delta implies this particular clause. So let me try to prove this. Right? So we had these two, right? Say not of A, not of Y, and Z, not of A, not of Y, and not of Z. So from this, what we can infer? We can infer not of A, not of Y, and we had another clause that is not of A, not of X, and Y. Now these two we can combine to get not of A or not of X. So this is implied. So that's why. Now let's see that if we add this to our knowledge base, we can detect contradiction bit early, right? So I have to write the knowledge base again. AB, let me quickly write down the knowledge base. BC, not of A, not of X, Y, not of A, X, Z, not of A, not of X, Z, not of A, X, not of Z, then 7 we have got not of A, not of Y, not of Z, right? And on top of that, what we have done, we have added this clause explicitly. This was not there earlier in the knowledge base. Now, implicitly, we have got another clause, which is A. Why is that? Can anyone tell me why we are adding this A here, this unit clause here? Devojit? So my question is why we are adding A here? Any idea? Come on, can anybody respond to this? This is again very straightforward. Adesh? Hello?
Sir, for unit resolution.
No, unit resolution is fine, but you see, we cannot just do this. So first of all, whatever that is true, we can add that to the knowledge base. So this is a unit clause, but is this true? First of all, is this true? If it is not true, then we'll be getting contradiction at the first place. This should be true because we are making a decision that A is equal to true. Go back. We are making a decision A is equal to true. We are following this branch, right? So that's why we are adding that here, right? Now, if we add that here, so what we can perform? We can perform one unit resolution on this to get not of x, right? Now we can perform, say, unit resolution on this and maybe with, say, 6. So you get, say, x not of z, right? We can perform unit resolution with this and 4. We get xz, right? Then maybe we can perform unit resolution on this to get, say, not of z, and this with this we get z and we get contradiction. So in this process, you see, you're not doing any decision, not a single decision. So these are all inferred, right? So that means if we do this, if we add this to the knowledge base, we get the contradiction without performing any further decision, right? So that is why we are adding this. So that is the benefit of adding this empowering clause. So these are called empowering clauses. And also they are called learn clauses. Right. Now the next question is that how to identify such clauses.
Sir, I have a doubt.
Yeah, sure.
Sir, at which stage we are adding that empowering clause? Like we are going down the tree, like you added a equals to true, so we are choosing that path, and exactly at which stage we are adding such clause?
Okay. So actually that is the kind of question that we are discussing at this point. So this is exactly the question that we are discussing at this point. Thank you for
Okay,
putting this up. So basically, we will try to add these clauses each time when unit resolution discovers a contradiction. So when we'll add this when unit resolution discovers a contradiction. And whenever we have got this kind of situation, so we have an opportunity to discover such clauses. And that's why also, as we are getting or deriving these clauses based on the trigger, which is conflict, these clauses are called conflict-driven clauses. Or simply, we can also call it as conflict clause. Now, what is the kind of motivation we have? The motivation is that if we add these conflict-driven clauses, add these learned clauses, then this will allow the unit resolution to detect contradiction earlier. Now, after we have got these learned clauses, so next thing is how do we use them with NCB? So this part we have intuitively talked about, but let us try to find out some formal way or methodological way by which we'll be doing this. And the method by which we'll be doing this is what we call as conflict analysis. So what conflict analysis does, it tries to identify the conflict-driven clauses. And how does it do that? It basically keeps track of the trace of repeated application of unit resolution. And this particular trace is represented using a data structure which we call as the implication graph. We'll get to know why we call this implication graph. So let us first try to define this implication graph. So let me first draw the graph and then explain why do we call this as an implication graph. So what I'll be doing, I'll be going back and forth. I need this, right? So basically, what we are doing, we are assigning values at different levels. So at 0th level, we are assigning a value true to A. So we are making a decision here. And this particular event is represented as a node in the implication graph, right? Then what we are doing, we are assigning in the first level. So 0th level, we have assigned A equal to true. In first level, we have assigned B equal to true. Again, this is a node here. In the second level, we are assigning C to be true. This is again our node here. And in the third level, we are assigning true to X, another node. So for every assignment, we are creating a node at every level, right? Now these nodes can be of two types. One type is a decision node. So whatever nodes we have talked about till now, they are decision nodes because we are taking our decision here, which we might need to revise later, right? Now, let us try to combine two decisions. One is A equal to true and X equal to true. So we are combining these two. So as we are not making any decision, we are just applying unit resolution here. So we are not moving to a different level. We are at the same level, the third level. And what we are getting in the third level, we are inferring y equal to true. You can go back to the knowledge base and check, right? We are assigning x to be a to be true and x to be true. So these two becomes false, and that means y has to be set to be true. And that we are doing with the third clause, right? So this is this node, this type of node is called the implied node. So, and the edges will be labeled with the clause by which we have derived this implication, right? And this is more or less the strategy that we'll be following in the implication graph. So you have a node here, right? Now, given this, we can also combine this with this decision, right? So if we do that from clause 5, which you can check later, we are at the same level because we are not deciding anything. We are not going to a different level then. So you can infer, or this can be implied, that z equal to true, right? Now we can use this use this, and of course use this to derive the fact that at the same level we are getting a contradiction. And we are using, I think, the 7th clause to do this. Now, I think you understand why I am calling this as implication graph, don't you? So we are keeping trace of the unit resolution, and whatever things that are being implied, we are representing that in a graphical structure. So that's why this is called an implication graph. And essentially, in the inference perspective, what we are getting, we are basically performing this. We are performing this conditioning: A equal to true, B equal to true, C equal to true, and X equal to true. And as a result, we are getting a contradiction, right? Now let us see what is the benefit. What is the implication graph if we add our empowering clause? We are adding this to the knowledge base explicitly. So what do? We start with 0th level, as we did earlier, assign A equal to true. And as soon as we assign A equal to true, what we can imply from this? We can imply from this is that X should be false, right? We are not making any decision. So we are at the same level, 0th level, and setting X equal to false, right? Now we have got this node and this node. Now we can use this too, and from clause 4, I guess. So you are setting A equal to true. So this becomes false. This is false and Z must be true, right? So we have to set Z equal to 2, and this will be again at the 0th level, right? Now, as we set Z equal to 2, we combine this, and this. And we can use the clause 6 to infer at the same level that we have a contradiction. So you see what is the kind of benefit that we are getting if we use this learn clause. We can detect contradiction pretty early than the original implication graph, right? So this, what we are doing here, we are conditioning delta over only A to get a contradiction. We don't need to do this conditioning. We just condition into over A, we know that we have a contradiction, right? And this is basically the trace of implication. Right. Now I'll remove this part because I need to do something else on this. Okay. Now let's say we have got this, what do we say, the implication graph. But what was our motivation or objective? Our objective was to derive the conflict driven clauses, which we have not got yet, right? So let us try to talk about how do we really get this, right? So I think we can take a very quick break for 5 minutes and resume this discussion later, right? We'll be taking a very quick break. Is that okay? So it is 9:05, so we'll start at 9:10.